Good evening, everyone. Today we are very happy to invite Lorenzo Bottizzolo to give an invited talk toward autonomous software-defined networks of wireless drones. Lorenzo is a candidate for PhD in computer engineering at the Institute for the Wireless Internet of Things at Northeastern University under the supervision of Professor Tommaso Melodia. He earned his bachelor's and his master's degree in computer and communication networks engineering from Politecnico di Torino, Italy. He was a research intern at Eternity Labs, research where he is now a collaborator working on integrating drone communications into the next generation's cellular networks. He was a software engineer intern at Google, working in the network infrastructure team. He was awarded with the Best Paper Award of the ECM workshop on wireless network testbeds, experimental evaluation and characterization, WinTech 2019, and the Electrical and Computer Engineering Outstanding Research Award 2020 from Northeastern University. His research focus is on software-defined control for wireless networks, MIMO systems, and wireless networks of drones. Lorenzo, please.
Okay, thanks Juan for the introduction. Let me share my screen. Okay, everybody sees my screen?
Yes.
Okay, great. So as Juan said, Professor Juan said, I'm Lorenzo from Northeastern University, and today I'm going to talk about, in general, wireless networks of drones, and more specifically, what are the steps that are being taken in the last years toward autonomous and software-defined wireless network of drones. Most of the work that I will present is just to give you a general idea of what drones can be used for in wireless networks. I'm going to also present some of the published work that I've been working on with Professor Guan and other members at Northeastern University, as well as in industry partners. So without further ado, okay, when we talk about drones in the wireless network domain, what we really mean with drones is wireless capable flying nodes. And these wireless capable flying nodes can have different applications in different scenarios. And we will take a quick look at three main categories of applications, and specifically we'll look at, as you see to the left, tactical sensing and report networks that very often are off the grid, and off the grid means not connected to cellular network. So those are scenarios where there's no cellular connectivity in a sense. We'll also take a look at aerial cellular users, where drones are effectively just cellular users that instead of being in a pocket of someone walking on the streets are flying up in the air. And to the right, you can see how drones can also be used to implement themselves flying cells. And we will see which are the enablers for such a technology, especially in the domain of the backhaul. Now, with respect to 5G spectrum that you see at the bottom of this figure, we can collocate these three, let's say, applications in low band, specifically for what concerns off-the-grid networks that need long-range connectivity, mid-band for what concerns the classic cellular use case, so whatever the carrier bands are below 6 gigahertz. For what concerns instead increasing network coverage and backhauling, we are focusing specifically on very high band of what you might have heard as referred to ultra wideband, right? So millimeter wave bands. We'll start from drones as aerial cellular users, and specifically, I will present a series of works that I have done in partnership with AT&T Labs. These works are essentially toward enabling high data rate 5G cellular links for drone source video streaming. Drone source video streaming can be especially instrumental in a series of applications. For example, live broadcasting and surveillance. Imagine a drone taking a live video of a TV news reporter instead of a helicopter, which is used nowadays. It can be used also for cargo and goods delivery. For example, the Amazon program on delivering packages through drones. Video streaming from the drone can be extremely useful in that case. In another business where drone source video can be very useful is infrastructure monitoring, where a company has to inspect a piece of infrastructure that is non-functional or broken, and instead of sending manpower on the field, can dispatch a drone in a much quicker and cost-effective way. Now, all these applications are essentially based on the fact that a drone can stream a video over cellular infrastructure, and there is someone else that is looking at this video and is taking action. Now, there is a problem when it comes to drone cellular connectivity, drone-generated cellular connectivity, because different than ground connectivity, where users on the ground often are in line of sight with one base station, maybe two, because they're surrounded by blockage, by obstacles that implement blockage to other cells. Drones that are up in the air, they are in line of sight with multiple cells at once. And while this is very good for, let's say, the signal that they want to transfer to their serving cell, this also causes great interference to the other base stations in the surrounding. And this, as an effect, degrades the performance of ground users around this neighboring cells. As you can imagine, this is not desirable from an internet provider perspective, because this effectively means that there is someone in the surrounding of where the drone is that is getting poor cellular service. We quantified this effect on an experimental testbed at AT&T Labs. The testbed is the one in the middle figure, and essentially is two mmBACs, and the four cells. We put one ground user connected to one mmB and a drone connected to the other mmB. And we measured the performance of the user when the drone was there and when the drone was not there. We measure up to 52% of the degradation when the drone was flying, with respect to when he was not flying. And this gives you a sense of how harsh the interference consequences are when connected drones are flying up in the sky and are streaming data at high rate, for example, streaming video. And the way this is patched nowadays is by limiting the resources allocated to drones. So this way, drones cannot quite stream a very high data rate, which preserve the ground-based cellular paradigm. But at the same time, this limits the whole applications that we talked about. So there is no high-speed uplink connection for drones as of today. There is an intuition that we had, and I'm going to talk about this in this slide. And the intuition comes by putting a directional transmitter on the drone instead of omnidirectional traditional transmitter. So a directional transmitter, for the ones that do not know, is essentially a piece of hardware or a software mechanism that directs the transmission toward a certain direction in space. We noticed that by directing the transmission in certain ways, we will see performance differences in the ground users that were around the drone. We also noticed that changing the position of the drone within its serving cell would also change the performance of the users in the surrounding. So based on this intuition, we came up with a problem statement of a drone willing to stream a video of a certain point of interest, and the network operator having to come up with a solution that is essentially controlling the drone location, the drone directionality of its transmission, and the drone serving cell, such that we can support video streaming without degrading the performance of the users in the surrounding. The proposed approach kind of looks like that. It's a closed control loop in which a drone essentially is willing to video stream from a desired point of interest. It communicates this point of interest to a controller that is at the RAN infrastructure, at the radio access network infrastructure. And the information that the drone gives to the RAN controller are which the point of interest is, which is its desired data rate, and what is the maximum distance that the drone wants to be from the point of interest. Now, the ground controller at the infrastructure is a sort of a late trend in cellular networks, and can benefit of a holistic view of the RAN network, so number of beats in the surrounding, their locations, but also their traffic load. So how many users are connected to one node rather than how many users are connected to another one. All this information can be used to solve an optimization problem and to come up with a solution, which is a optimal location in an optimal transmission directionality. These two information are sent back to the drone, which implements them. And this way, by solving this optimization problem, we guarantee drone capability of video streaming by minimizing the interference to ground users in the surrounding. We tested and evaluated this approach both on a small scale real world experiment testbed, which you see on the left. So we placed 3 base stations, 3 users, one of which is a drone, and decided about a point of interest, and compared this approach with other solutions such as no control or optimal serving cell solution, which essentially points the direction of the transmission right at the serving cell. We noticed a throughput improvement about 19% while supporting the video streaming capabilities of the drone. We also extended our evaluation to a large-scale simulation thanks to the cell deployment of the carrier we worked with, and we obtained overall similar results, so supporting video streaming and overall reducing the interference of neighboring to neighboring ground users. So what happens if the network conditions change or the point of interest changes, right? Let's say a drone wants to stream a certain point of interest, and then its mission changes, it wants to stream another point of interest. Well, this is very simple. It just repolls the RAN controller at the infrastructure, asks for a new solution, and implements a new solution, which is essentially a new location in space and a new transmission directionality direction. But how do we move from one location to the next optimal location? This is another problem that we decided to solve. So in a way, how do we make sure that when we move from one point to another, we have the best performance for the drone, but also we are conscious about the interference caused to the ground users? So the intuition is similar. So we have seen how directional transmitters can help in this sense. And another approach we took is, instead of moving in a straight line A to B, we decided to take a interference considerate approach. So to moving from A to B in a path that considers the interference along the way. And we proposed a new approach for trajectory control, which is very similar in a way to what I just proposed, but essentially the mechanism is the same. So it's the drone asking for a solution and the controller giving that solution. This time, the solution the drone asks for is the path from a point to another, the optimal path from one point to another, and the directionality of its transmission to be implemented along the path. The goal is still the same: maintaining high-speed connection along the path while minimizing uplink interference. And I'm going to show you here what the results look like. So this is a plot where the red dots are base stations essentially, and there are 2 points A to B, and the power level you see there is essentially the interference power to this base stations the drone is not connected to. If we take a straight path, and this is it, even though the plot is 3D, so it doesn't really look like a straight one, the interference is a certain level. With the proposed solution, we kind of take a different path to minimize the interference and optimize the drone video streaming capabilities. So you see here to the top, this is a non-optimal approach. On the bottom is what we implemented. So a different route from the very two endpoints A and B. For this specific example, we can guarantee up to 9.5 dB interference reduction along the path, which is pretty remarkable, I think. We also extended our evaluation to large-scale simulation, but without digging too much into the numbers here, what I want to show is that this approach is beneficial in different environments, different LTE bands, whether this is in a rural area or an urban area where more base stations are. And we also quantified how impactful this might be when not one drone, but maybe 10, 100 drones are up in the sky. And as you can see from the plots, this is still pretty remarkable. It is more needed when more drones are up in the sky. So I'm over with drone connected cellular users. Now we can move on onto off-the-grid networks of wireless drones. And specifically, I want to present a work which is called SwarmControl, which is about automating distributed control for self-optimized drone networks. This is a joint work with Air Force Research Lab, which is also the funding agency for this project. And in a way, Professor Guan was also heavily involved in this one. So what are off-the-grid swarm networks and why they matter, first of all? So off the grid, you have to imagine a drone that has no connectivity a drone network that has no connectivity by itself, but in a way has to come up with a network solution to have drones of the same network communicate with each other. And what are the applications that a drone network off the grid might implement? It can be, for example, used as an extension to cellular network. So connecting ground users effectively instead of using cell towers, using a flying network of drones. This can be very useful in disaster scenarios where the cellular infrastructure just crashes and it's not there anymore, or as an alternative to an untrustworthy ground cellular network. Another example is on-demand tactical networks. So this is a military application where a flying network of drones could implement a search and rescue mission. In this case, there is no cellular connectivity. You can imagine a remote place, in the desert where there are no cell towers, and a drone network will have to implement its own connectivity. Another example could be an on-demand security flying network with search and track tasks. For example, to implement distributed surveillance, such as tracking all the red vans in a certain area, right? We've seen a couple of examples, but the problem that we're trying to solve here is how to control such a network and how to control it in a programmable way and make its operation optimized. Now, I'm going to list a few challenges here of why this is an important problem to solve and why it is not trivial. The first one is the need for a distributed control approach, right? When we think of drones today, most of the time we think of something like this. There is someone with a remote control somewhere telling a drone where to go. And for one drone, you need one person. And for 5 drones, you need 5 people. And the more drones you have, the more people you need. And this, of course, is not scalable. You cannot think of a drone network in the desert made of 100 drones, having 100 people there to control each individual drone. This is just an approach that doesn't scale. So a possible approach to solve this is to use a centralized control. And a centralized control, you can think of a single server somewhere that is connected to one of the drones, and this drone kind of relays the information to the next one all the way to the last drone. And this way, all the drones can kind of talk to the network controller, and the network controller can tell the drones what to do. Now, there is a problem with this approach. And the problem is that the latency between the network controller and a drone up in the sky can be very long. And this means that the controls that are given to the drones can take time to be implemented. But most importantly, it means that the network state information that is only available at the drone takes time to travel to the network controller, which when, let's say, implementing a network solution and sending it back to the drone would result in a solution that is not reflective of the network state anymore. So this is, let's say, this loop that you see here with the green arrows is the loop of network state information being sent over the network operator, which computes as a network solution, sends the control backs, but when the control come back, they do not reflect the network state anymore. So the approach we took is the one of distributed control, where we still have a network operator, and we will see later how this works, but the control are distributed and each node implements its own control. A second challenge is how to implement the control logic, right? How to tell the drones what to do. The approach we took is to implement the control logic once from the network operator, and then take distributed control actions on the drone. In a sense, this happens through an interface, and this abstraction interface serves the network operator that can define a general control objective for the overall network without knowing how many drones out there or how to actually implement this. Imagine a network control objective can be maximizing a certain network performances rather than minimizing the overall network power consumption. Very high level objectives like that. Through this abstraction, this general control objective gets decomposed in distributed control problems. We'll see more of this later. Another challenge is, can we guarantee optimality of the operations? In a way, how do we make sure that our network operates at its peak and the network parameters are being optimized for a certain goal? We also take care of this part in the generation of the distributed actions. In fact, when we take the general control objective and we decompose it in distributed optimization algorithms, which when solved, guarantee optimality of the network. The last challenge is about network programmability. Now, I showed you a way to program a network, but how to reprogram it? How do we override our previous network behavior if we change our mind? So this is very simple. You can run, the network control procedures more than once. So you can give a control A at a certain point. The second point in time, you can change your network behavior. You run the same thing once again, and new distributed optimization algorithms get sent off the drones. You can run it a third time and a fourth time and so on. So this, in a sense, can happen on a large time scale, maybe every 5 or 10 minutes or an hour. It's not a problem, and it's already supported by this framework that is called SwarmControl. So to solve the control problem that I stated before, SwarmControl implements automated distributed control for self-optimized UAV networks. The SwarmControl framework is something that kind of looks like that. I'm not going to go very much in detail. I just want you to get a sense of its operations and maybe not its implementation, but essentially it composes of two big chunks. One is the control framework, which is the orange boxes that you see on the top. It is a framework that is interfaced by the network operator. Another piece of SwarmControl is the drone programmable protocol stack, which are the green boxes that are installed at each drone. So what the control framework does is taking an input from the network operator and coming up with distributed optimization problems that are sent to the drones. What the drone protocol stack does is taking this problem, solving them in real time, and implementing the solutions that reflect the dictated behavior by the network operator. So we have a centrally defined control, but distributed actions to implement it. So let's take a quick look on how the control framework works, and then we pass to the drone protocol stack, and then I'll show you a video of this taking place. So the first box that you see on the top is what we call control interface, and it is a natural interface that a human being can type into. And we pre-program some network behaviors. So this interface is essentially a way to select the desired network behaviors. There are some pre-programmed. There is the possibility to implement your own network behavior if you have specific requirements. But as I said, control problems can be maximizing the network throughput, maximizing the log network throughput, which takes fairness into the equation, or minimizing the network power consumption and so on. Classic network control problems. The second box you see there is the network control problem construction. So this, let's say, defined network behavior gets translated from words into mathematical equations. And this is done thanks to a UAV network abstraction. This mathematical formulation gets then decomposed into distributed control problem in a distributed solution algorithm generation step. So after these 3 steps, from a very high level input, we come out with individual distributed control problems that can be sent to the drones, okay? So taking a look at what happens when these problems get sent to the drone, we start talking about the drone programmable protocol stack. As I said, this is in charge of solving distributed control problems and implementing them in real time. The way to do it is through its 3-plane design. We have a decision plane, a register plane, and a data plane. And each drone implements the very same programmable protocol stack. So the decision plane that you see on top is essentially in charge of solving the problem. So it contains mathematical solvers that solve distributed optimization problems and come up with a solution. Each layer, if you're familiar with the TCP/IP protocol stack, each layer has its own distributed control problem to be solved. And among these layers, we also introduce a motion layer, which is controlling the physical location of the drone. The data plane implements this TCP/IP stack together with a new motion layer. The motion layer interacts with a flight controller, while the physical layer interacts with a radio. And those are the 2 layers that actually, implement something in wireless or in motion. The rest is the classic TCP/IP stack. In the middle, there is a register plane, which serves as a middleware, storing solutions for the algorithms being solved and storing network state information from the data plane to be passed on to the decision plane. So for example, if we want to solve a layer 3, so network layer optimization problem, we most likely need information about which next hops are available in the surrounding toward the destination we want to reach. It's a classic network routing problem. This information is only available at the data plane, which is aware of which nodes are in the surrounding. This information is put into the register plane. The decision plane takes this information, runs the optimization algorithm, and writes back into the register plane what the next stop should be for a certain destination. The data plane takes this information and implements it in the protocol stack. So that's the overall logic. Passing to the prototyping, I'm not going to dig very much into details, but that's kind of the prototype that we came up with. It is a Intel Aero drone, which is one of the smallest drone out there, to be fair. We mounted a software-defined radio on top, which served for our radio front end, and 2 additional antennas for that. On the bottom, it's the software hardware schematics of our prototype. And we tested SwarmControl on a couple of network configurations where we employed 8 drones in 2 scenarios. You can see here scenario 5 and scenario 6 are somewhat similar. There are 2 source nodes that want to deliver information to 2 destination nodes. That's the overall mission, right? And they employ 4 relay nodes to carry this information in a multi-hop fashion. So this is our network. Now the question is, how do we want to control it? What behavior do we want our network to implement? And how this behavior is effectively implemented through SwarmControl, right? We tested this on 4 network layers. So despite this approach can be implemented on all the network layers if you want. What we implemented as control variables are 4 control variables belonging to those 4 layers. So layer 0, the actual physical location of the drone, is our control variable. Physical layer, the transmission power of the radio, was our control variable. Routing, the next stop toward the destination is the control variable. And transport, we implemented that TCP-like congestion window session control, where the size of the congestion window was our control variable. So we have those 4 control variables that we're trying to optimize in real time on a distributed network. The place we tested this is a facility we have in Northeastern, which is pretty cool. It essentially is a big Faraday cage that is coated in foams such that it simulates free space propagation environment, which is ideal for flight testing. The results kind of look like that. So you see on the left, sorry, let me introduce the control problem first. For these 2 examples, we decided to control our network, telling the drones to maximize the sum throughput over the overall network. So this is what we're measuring in the plots. Plots to the left measure the overall sum throughput of the network, and plots to the right show the locations of the drone changing in time to achieve that goal. This is a snapshot of our experiments. We can see there are the 2 sources to the right, the 2 destinations to the left, and 4 nodes that relay the packets from sources to destination, A, B, C, D. And here are some average results, which are pretty good, pretty remarkable results. We compare with other control schemes, but I don't want to spend too much time on what we compare our approach with. Bottom line, when we control multiple layers in a distributed fashion, getting rid of the latency that might come from having a central controller, we can achieve very good results. So here there is a video of the experiments. I'll try to pause it and explain what exactly is going on, so maybe you have a clearer idea. And also maybe use the best quality. So this is the facility I was talking about. It's a pretty big chamber. It's almost the size of a tennis court. We removed the pads from the floor, and this makes takeoff and landing easier. Let me pause the video here. What you just saw here to the left is the control framework, the orange boxes that I showed you a few slides ago. And what happened in this less than 3 seconds is that a network operator picked a control problem to implement. That's in a yellow box there. We picked one, rate maximization. We could have picked a different one. It didn't make a difference. In the blue box, SwarmControl has mathematically constructed the control problem. And in the red box, this control problem has been decomposed in distributed optimization problems that are sent off the drones. So this whole thing happens in a matter of seconds. And it's after this, the central controller doesn't play a role in this anymore. Cool. So what happens from now on is that the drones start their operations, and they all have these distributed control problems that are running, right? There is a first network formation phase, and when the data transmission starts, the individual nodes are optimizing their network parameters in real time in a distributed fashion. So despite the fact that you cannot see the TCP congestion window being optimized in this video, I want you to focus to the location being optimized. And you can tell from the video that the drones are going through iteration loops, optimizing the location and then optimizing it again and again until they reach convergence. And that's what the optimal state for the network is. So when they reach the optimality, they stay there and continue their performance. So from the top, you can see a little better how the different iterations go. And this snapshot here shows the network performance that are being achieved in this very moment. So when the mission is over, the drones land, and that also is concluding the video. So that concludes off-the-grid network of wireless drones. Now we're going to talk about applications that involve drones to increase cellular coverage, but more specifically, we're talking about the enablers for implementing cellular coverage on drones. This is a work that is a couple of works that are in collaboration with Facebook Connectivity, which provided the radius, and some of the works they also involve previous people from previous works. You probably see the same people twice in these works. And the first one I wanna present is about experimental millimeter wave channel model for UAV to UAV communications. So why are we talking about millimeter wave for drones? So as I said, UAV networks can be used to provide connectivity, to provide cellular service to ground users, and this can be applied in different domains. Rural connectivity, where there's no cell deployed yet. Capacity scaling, for example, providing connectivity in crowded events, such as stadiums or festivals, where the network capacity is being saturated by users there. Or emergency scenarios where the ground infrastructure collapses and we need to find an alternative way to provide service to people on the ground. So all these applications rely on the fact that drones can communicate with each other on very fast links, and they can route the traffic toward a peripheral base station or somewhere into the internet, also at very high speed. So there is a need for high capacity wireless backhaul. This is a term that essentially means routing traffic into the internet. And the technology that came out in the last years is called millimeter wave communications. And it's been rolled out with 5G deployment. Most of the US carriers are already having millimeter wave base stations out there. But essentially, millimeter wave communications, for the ones that are not very familiar with it, are very, very fast communication, but also very, very directional, okay? So the wireless channel is very different from what is called sub-6 gigahertz. This technology range from 30 to 100 gigahertz. And for this reason, they are kind of being, they're still under study, and there is a big effort from the wireless community into coming up with new models, new algorithm specifically for this band. So while terrestrial millimeter wave channel is somewhat new, as I said, there are cell phones that already operate at that channel. There is a full standard at that channel, and some carriers already provide that. Millimeter wave in the air, so drone-to-drone millimeter wave channels, are somewhat unexplored, and this is because we can just not apply the models we have for ground millimeter wave channels to drones. And why can we not do that? So as I said, first of all, millimeter wave communications are very directional. This also means that a tiny movement of one of the two endpoints of a link can have a very big impact. So while nodes on the ground are mainly steady, they don't move very much. UAVs flying in the sky, you can imagine they have quite a bit of movement, even though even when they fly in positional lock. Other reasons are, for example, the directionality of the transmission of the radios when they're mounted on the drone. Sometimes the drone tilt to move, and this also can create some problems to the millimeter wave channel. A second point is that different altitudes have different oxygen levels. And why do we care about this? Well, at some frequencies, oxygen absorption of the wireless signal is a serious problem. So this is something that has to be analyzed yet. And third, when we mount a radio on a drone, we have to consider that the drone itself has a frame that can bounce the signal off, can create shadowing, and depending on the size, the material of the frame, we might experience different propagation paths for the millimeter wave channel. So with these assumptions, what I want to say is that we need a millimeter wave channel model specifically for drones. And we have come up with a experimental channel model that factors in all these effects that I've listed before and comes up with a all-in-one path loss formula as a function of distance as traditional path loss models. We derived this model, as I said, through experiments. So we run many experiments, collected data, fit this data into a path loss curve, and come up with a single equation solution that hopefully is the easiest way to implement or opt in a millimeter wave drone model into a study. We also compared what we obtained with the terrestrial millimeter wave models, and we made the code available at this GitHub repo. So anyone that is willing to perhaps derive different models for different circumstances can take a look at our data and compare. The prototype kind of looks like that. You see top left is a DJI M600 drone mounting the millimeter wave radio, which is that white box you see there, which is provided by Facebook. And the picture to the bottom shows you that a little bit of our deployment scenario. So we have two of these guys, and then we have a ground controller which tells the two drones where to go and tells the radio what to do. Essentially, we covered this many points in space where the red ones are the position where the transmitter was located, and the blue ones are the position where the receiver was transmitted. The two radios are facing each other, of course, and we run a total of 27 altitude distance pairs. Each pair was a scan of 400 beam pairs. For beam pairs, I mean each radio in millimeter wave bands have a direction where to point to. This is called beam. So when two nodes are talking to each other, they both have to pick a beam, and depending on how aligned those beams are, you get a better or worse communication. So we scan all the beams of all the radios and come up with models for the best beam, which is the central one, since the two radios were facing each other, but also for suboptimal beam selection, which is pretty interesting. So without knowing you guys too much about what the measurement was like, this is a video that shows a little bit of the experiment in collecting these measures. And essentially, as I said, we took two drones, right? Identical. So they both mount the same radio. One is the transmitter and the other one is the receiver. And we kept collecting data. This is the facility that we have in Northeastern, which is next to the facility that I showed you before. It's an outdoor cage, which is really ideal for flying drones. And perform drone experiments. The tethering that you see, as I mentioned, is powered for the radio and Ethernet cord for the radio to tell the radio the wireless operation to implement. So anyways, we performed this very experiment that you see for all those data points that you've seen on the map. Okay, and we came up with this fit. Essentially, we realized that despite we run measurements for different altitudes, the altitude, at least between the ones that we have run, doesn't really impact the path loss. However, the shadowing changes a little bit. We also performed measurements for suboptimal beam pairs. So what is the path loss when the two radios do not operate with the best beam selection? So what if the algorithm that is selecting the beam does not select the optimal one for any reason, right? This can be just a bad algorithm, or can be due to certain circumstances. What does the path loss look like? So we quantify the gap between the best path loss and the second best or third best, and so on. And we came up with this formula, which is a classic path loss formula, this is very specific to UAV millimeter wave communications. So once we have this millimeter wave model, whatever, we can, we can think of a little bit more of what a flying cell application might look like. This work is taking a closer look at that. It's called mmBAC, and it's about location-aided millimeter wave backhaul management for UAV-based aerial cells. And we've seen, I already introduced you to this concept of aerial cells that are used to provide service to users, and how the millimeter wave connectivity can provide backhauling, very fast connectivity, but also very directional. So the problem that we're trying to analyze in this work is when a drone decides to turn on a cell, has to set up this millimeter wave backhaul link. And the time of setup is very critical, because this is a blocking for providing service to the users on the ground. So the faster, the most efficient way we can set up a millimeter wave link, the better, the sooner we can provide service to people on the ground. And the way that normally a millimeter wave is set up, as I mentioned, is given that the two endpoints have beams, there is a first phase that is called scanning. The two endpoints scan all their beams, okay, and take measures every time a single pair of beams is being analyzed. And after they scan them all, they pick the best and they use that one for communication. Now we're trying to come up with a smart way to speed up this process when we implement a drone to ground communication. And the idea that we had is to use the GPS location of the drone and the fixed location of the node on the ground to have a central beam pair that can be used as a start for a more refined search in the surrounding of the central beam pair. So in a way, we used site information, which is GPS location, to initialize the link establishment in millimeter wave. And the algorithm is very simple, and it kind of goes like that. The ground node knows where it is, and the drone knows where it is by the GPS coordinates and the GPS positioning system. They can calculate a relative location, relative direction that they have, and they can use that direction to identify a central beam pair. From that one, they can only scan the surrounding of the central beam pair and actually take measurements and pick the best. Once the best one is picked, they can use it for data communication. Now we compared this approach with not the exhaustive scan, which is the brute force approach, but what is often implemented is what is called multi-tier scan. So multi-tier scan essentially picks a sample of beam pairs, one side and the other, measures their performance, picks the best, and goes for a more refined search there. So compared to that one, we could reduce the link establishment latency from almost 20%, which is the gray line that you see there, to around to less than 8 seconds. So to 20 seconds, from 20 seconds to less than 8 seconds. And this is pretty good, because you can imagine you have so much more time to actually use the channel, while other approaches just use that time to set it up. And we did prototype and tested this in real world. You already seen the schematics in the previous work, but essentially this time we only use one drone, and the other node is mounted on a tripod. And why does this approach matter in mobile network? Well, when we implement link establishment on mobile network, mobile networks change very fast. For example, here we have a drone that relocates multiple times, and every time it relocates, you have to re-establish the link. So you can imagine that a drone that relocates often can benefit very much from this approach. So what we have seen here just taking place is essentially the algorithm that I just explained. And once the drone relocates to a new position, we have to re-establish the link again. So what happens is that the two nodes kind of know their relative positioning and select the master beam pair. This case is 27, 27. Then they scan the surrounding of this master beam pair, and they pick the best measures. For example, in this case, it's 28, 29. That's the best measure beam pair, and they use that one for communication. So you can imagine now the drone serving cells on the ground and using the mmWave link on those beams for backhaul. Once the drone relocates, and this can happen because people move or other reasons, you have to rerun the same thing. And this goes on for a few more waypoints. I think you got the idea. All right, that's a nice landing. So I'm not sure how to. Okay, so what are the takeaways of this GPS aided link establishment for mmWave aerial networks? So the fact that we can, if we employ site information such as GPS, we can reduce the link establishment overhead by 66% in our case. And this means that you can use the channel 66% time more. At the same time, the SNR of the channel doesn't significantly drop for the experiments we run. So we can achieve similar SNR results whether we employ our link establishment procedure or the multi-tier scan. Talking about spectral efficiency, as you might understand, the more often a drone relocates, the more often you have to reestablish link, and the more important it is to establish the link fast. And this figure kind of gives you the idea that a drone that relocates very frequently is especially careful about implementing effective link establishment procedures. So this was the last topic I wanted to talk about today, and I hope you got an overall idea of what network of drones can do, what their applications are, and what are the bands that they work at, together with a series of challenges that are very specific to applications or wireless bands.
Okay,
so
thank you very much,
Lorenzo. Questions about what I presented to you today, or you want to know a little bit more about certain topics, we can talk about it now.